Well, looks like we can start. Welcome back, folks. Smaller class today. Last time we had a big Zoom class, but we'll do the best we can with the people we've got. Hopefully others come in later. But for today's class, we're going to finish off chapter 13. We're basically there. We are on the last part of the very last problem. We just didn't want to completely rush through that last bit at the last few moments we had last class. So we're going to just kind of refresh what we did in chapter 13, looking through that problem, finalize it. And then we're off to chapter 14. And the crazy news about that is, if you look at the syllabus, this is the penultimate chapter. We're only going into chapter 15. 15 is kind of a big chapter, but we're just about there, folks. Also, when we complete week 12 next week, that's the 75% mark. So definitely we're getting through the semester. Any questions at all then to start us out today? Okay, as you can see from the scribbles that are on the Canvas webpage here, our methods in chapters 13 and chapter 14 look pretty similar in format. The difference is if you're dealing with a proportion, you're by its nature working with categorical data with categories successes versus failures. And so that's why the parameter, the proportion P, is what we're estimating. We move over to quantitative data in chapter 14, we're estimating a parameter mu, the population's mean. The intervals are pretty similar. You start off with the estimate for the unknown. Estimate for mu is the sample's mean y bar, just like the estimate for p was a p hat. Then you take a critical number. In the prior chapter, it was a z star as our critical number that multiplies by a standard error, and this is the width of the interval, or half the width really, because we add and subtract it for the full width. We call this the margin of error, and here it has the same kind of format. Standard error formula is even nicer to calculate. It's more straightforward. But the thing that makes chapter 4 a good one to do after chapter 13 is there's actually a lot to talk about when it comes to the critical number T star. We have to compute it from scratch every single time we do a problem, essentially. Whereas with Z star, it's just a table lookup for the standard levels of confidences that would be asked as quizzes or exam questions. So this is what we're getting through. The quiz number 9 is just based off doing another chapter 13.3 problem, so another confidence interval procedure. Another thing to mention before I forget is exam 3 is going to be right before we go on the break. So Monday, November 17th, and the information's already posted. Pretty much it's right up to chapter 13, including chapter 7 and 10. Well, I think that's about where the end of the announcements are. Any questions or comments at all, folks, before we get started? Okay, well, let's move on into the next portion. Here's where we left off. Again, we were nearly done, but just a refresher of what was going on in this problem. Let's go to the very top of it. We're studying this data here from May 11th, 2008 of 143 individuals who had a hip replacement with ceramic hips that were installed between 2003 and 2005. A success was the outcome that the hips squeak, so that's why we define this parameter P right here. Let's grab this real quick. Part A, just like in this chapter and in the very next chapter, is the crucial step to get your conclusion just right. We try to be pretty careful when we write down that parameter. But next, we just take a look into the 10 successes divided by sample size. They gave us the sample's proportion of successes. We threw it into the standard error formula and got 0.0213. After condition checking, we just put this all together. 95% confidence gave us a table lookup of 1.9600. And then plugging in those three quantities, we got the interval. And we didn't do this on every problem. In fact, this is the only one we converted into a percentage. And this was just a way to mention there's more than one way to write down your conclusion. You could say population proportion. In that case, you would just leave it as the actual proportion values. But if you go with population percentage, it's up to you. We'd be using these percents here and here. But watch out for the instructions in MyLab statistics. I think more often than not, they want their proportion values. So this is just an alternative way to give a conclusion. So as far as that practical interpretation goes, we interpret the confidence interval by first starting with the level of confidence. We'll say we have 95% confidence that. Next step we take is just go back to the confidence interval and interpret this entire inequality. We have to really write out what P is one more time. And I know it's kind of redundant. I think I mentioned before, even though it's redundant, I found that people on exams and quizzes, particularly on exams, are tremendously more accurate with the conclusion part F if you wrote it down the first time. So even though it's painful, I ask you to write it down twice. Sorry about that, but it gets you through part F pretty cleanly. So we'll say we have 95% confidence that the population percentage of squeaky hips among all people with a ceramic hip. And let's keep on going with the procedure done between 2003, 2005 with the procedure done in or done between 2003 and 2005. Okay, so that's a big run-on statement so far, but we're saying the percentage of squeaky hips among that particular population is between 2.8% and 11.2%. So finally, that's the end conclusion to this problem. If they repeated the study, they would want to use the same exact sample size in the sense that if we repeat the study 100 different times, we have 100 different confidence intervals, and we expect 95 of them to successfully capture this unknown parameter P that we identified. So that's the whole statement. We just link up part A with the interval that we found in part E to conclude the problem. Well, any last questions at all, folks? Returning to this one. Okay, well, we did it. This was, again, the big thing that we were trying to discuss and really investigate all the way back in chapter 1. This will be the last time we take a look into it, but it's kind of fun to reflect just how much stuff we've done from the very first day of class. In the very first day of class, this is the same stuff we were talking about. In fact, if you really wanted to, with the made-up data I put here in purple, you just run a whole confidence interval problem with this stuff. When you identify a population and its categorical data, you collect the statistic p hat from the sample, which you hope is random. Then this was our whole problem. The reason the course is so long, the reason we have so many methods, and really the whole reason we talked about the normal distribution in the very first place in section 5.4 is the way you describe that error is through the whole confidence interval, like we did here. This part, z star times standard error p hat, is the error in estimating the unknown parameter p using p hat itself. So we finally hit that objective, but we want to do it again. So we're now going to go to the quantitative data next. Any last questions at all, folks, before we close out chapter 13? Okay, well, chapter 14, it just comes in as just one overall section that we're going to look into. As far as the reading goes, the reading indicates that you can skip the last two sections, 14.4, 14.5. They're pretty cool topics, but they go beyond the scope of our course in this class. So the reading is really 14.1 to 14.3. But it's the same kind of ideas we saw before. So in a certain sense, it's kind of a more compact section than chapter 13. But there's still a lot to discuss when you change over to quantitative data. So here's how it starts out. First, let me close this one as well. Like a lot of sections in this book, a lot of chapters in this book, starts off with a wall of text, but everything's color-coded in the same kind of ways we saw before. We're looking into the differences between a population. Population is everybody we want to study, the entire collection of individuals or objects. Parameter is something that describes a population. So really, this is all just review so far, but these things are pretty complicated in statistics, so it's good to kind of refresh ourselves on these things. What the parameter is and what the statistic is depends on your data type, whether it's categorical or quantitative. So going down the notes, likewise, a sample is a part of the population you select for study, hopefully randomly. Statistics are what describes a sample. Didn't mean to do that. There we go. And in the rare case, I think I only had one example this entire semester that you have a census. You don't have to do any of this stuff. The census will describe the population completely. And so we don't need inferential statistics at all. But that's rare. And so now here's what we'll have to do in almost every other situation in practice. For just a roundup of notation, n is the sample size. It's been a while since we really dealt with these statistics, but they're coming back. Y bar is the mean of the sample. S is the standard deviation of the sample. And you can go back to chapter 2 on just how we calculate those things. We majorly made the calculator do the work for us and then interpreted what they were trying to say about the data. Y bar is the center of the data. We hope the data is symmetric, so it doesn't move too much in one direction or not, according to skew. And S is going to describe the standard deviation, how spread out the data is. But that was another purpose of chapter 5. It gave us a good way to think about what is the standard deviation doing for us in terms of spread. And that was the section 5.3. 689599.7 rule. So it's kind of easy to say what the mean does. It's the center of the distribution. But the standard deviation S obeys this rule. Approximately 95 observations are within 2 standard deviations, whether that's the sample standard deviation or the population standard deviation, the mean. One standard deviation will contain a roughly 68% of the sample's observation or the people in the population. So next are the parameter values. Mu is the mean of the entire population. Sigma is the standard deviation of the entire population. And we have these same kind of estimates as before. Also, same kind of statements as before. Let's make these statements first. Mu and sigma are unknown. So that's our whole problem in statistics. Unless you gather a census, then you can calculate those, assuming you made no mistakes in the census. You actually included the entire population. We can still estimate mu and sigma. Mu can be estimated by saying it's approximately equal to the mean of the sample, y bar, and sigma, the population standard deviation, can also be estimated by saying it's approximately equal to the sample standard deviation, lowercase s. So we have 2 parameter estimates that we would like to make. And in order to say the error in this estimate right here, this is why the problems get so large, we have to go a little bit farther. This is true, it's approximately equal. As the sample size gets larger and larger, that approximation gets better and better. But at any size, we must do the following. We must describe the error in this approximation. There's an error in making this approximation too. This is why we have something called the t-distribution coming into play. And this was different in, say, section 13.3. In section 13.3, we look at the central limit theorem. Notice the huge change we are making. In 13.3, there is one parameter, P. That means when you describe the central limit theorem distribution, the mean involves that parameter P, but so does the standard deviation. It's P times 1 minus P. There's really just one parameter in this family of distributions for the central limit theorem. That's why when you estimate with p hat, you're estimating two things. You're estimating the standard deviation at the same time as you're estimating the center. This is different though. There's two parameters, and this is going to make it more complicated for us, but still starts off in the same way. There's a central limit theorem in the background. The central limit theorem is always kind of like the most abstract thing going on in a statistics class. So there's multiple ways to think about it. First, there's this picture. This is talking about a sampling distribution of the statistic. It's essentially telling you part of the central limit theorem. And then there's this part. This is the central limit theorem directly. So this is a lot of reading all at once. Let's first look at the graphic, seeing it visually. Then we'll tie it into what this is saying. And maybe later on, maybe not today, we'll do another simulation in the big calculator to actually show a normal curve emerging as we collect more and more sample means. But just like in section 13.1, this was pretty abstract too. We were looking into how does the central limit theorem work. We have to do this all over again because it's a new scenario. It's a new statistic and two parameters now. So here's the new graph that's going to kind of describe that. First, let's look into the definition. This is tricky already on its own. Assume you're studying some population and it has a quantitative variable that you want to investigate. It could be time, distance, height, anything along those lines. We'll assume we have a simple random sample, and n is the sample size. It's from a population we wish to study. Then the sampling distribution of a statistic, say of y bar, that's what we're investigating here. The sampling distribution of a statistic is a probability distribution, kind of like a normal distribution, for example, that contains all possible values the statistic can take from a simple random sample of the target population. So that's a pretty dense statement, and it was kind of a similar statement in section 13.1. This graph below is to try to help us understand that entire statement above. So here's the population. The very next thing we do from that population is we take a sample of size n. Hopefully it's a random sample. A simple random sample is the gold standard here. And this arrow represents one study being conducted. Mu and sigma are the parameters describing the population. They're the unknowns. Once we do that one sample, this is sample one, we get the statistics values, y bar and s. So we have estimates for both mu and sigma. We're focusing on y bar when we're looking into the central limit theorem. And this one particular sample mean, it can be plotted in a collection. Here it goes, one little dot in the histogram. But now we imagine, and this could be done in practice if we had, say, like an unlimited budget, we could repeat the study. In fact, good statistics often do repeat studies under as similar conditions as possible. So imagine you did repeat the study, but insist that it's the same sample size each time. Here's sample two. It's a different group of n individuals. That means the mean that you calculate is still estimating the same exact parameter, and so is this standard deviation s, but that mean is not the same. It's a different collection of people. It can come out as a different value. So here it goes in a different spot. And then we can repeat this over and over and over again until ... we've, say, done this 1,000 times, maybe 1,000,000 times. Mathematically, that's something we can imagine. And mathematically, this is something that's actually proven from scratch, from first principles with probability. Repeat many times. Repeatedly, sample many times and collect all sample means into a histogram. This is the sampling distribution we're looking at. You know, this is a screenshot of a textbook. If you're curious, this is Statistics for the Life Sciences by Gentleman Samuels, page 150. Really, this is not exactly the sampling distribution. It's the approximate. For a picture like this, we're imagining maybe we sampled 10,000 different times. We have 10,000 different sample means. Some of them might have matched by sheer pure luck, but it's unlikely, even with 10,000 different repeats of the same study. Yet they start to aggregate in this nice shape. We know from our work with the normal distributions and in section 13.1, that looks awful lot like a normal distribution, right? You could put a normal curve to this. It would be a curve that's symmetric, extremely mound-shaped, and we have some expectations on this. This is well approximated by the normal distribution, and the center is the first thing we were trying to estimate all along, the parameter mu. Let me change my color coding though to match up with what's above. The center is right at parameter mu, so all these statistics that were being calculated, all the different versions of y bar, are just scattering around the center, the true unknown population mean mu. What we don't know, what the central limit theorem gives us as extra information is what the spread is. So we'll resolve that on the statement of the central limit theorem. But this idea is so abstract that we spend a lot of time on it, thinking of it. So it makes the central limit theorem seem less like a magic process that you put stuff in a calculator and get a result out. This is really something that can be proven if you had the budget to repeatedly sample, and it's something we can show in a simulation. Maybe not today. We'll refresh these ideas when we come back on Monday and look at a quick simulation. But here's the major takeaway. When you run a study with quantitative data, there are two populations. Population one is the one you're going to try to study with the two parameters you're trying to investigate. But the second population is where your statistic y bar even came from is from this right here with a normal distribution. There's two populations on the table. The sample mean right here came from the second one. The central limit theorem tells you what this is exactly, also describing the spread here. So that's a huge statement. Any questions about that so far? Okay, here's one thing that's really, really wild about this. Notice how little we talked about the population. If the population is symmetric, then this is automatically symmetric. If the population was normally distributed, it's automatically normally distributed here. But the central limit theorem that makes this extremely widely applicable is even if the population is skewed, if n is large enough, we need to say what's large enough. So we'll have a rule of thumb about that. But even if the population is skewed for a large enough sample size n, the sampling distribution is still approximately distributed normally.
That's what you showed us with that calculator, right?
Yeah, when we were section 13.1, even when we had skewed, if the parameter is too big or too small.
So
Exactly, yeah. The large enough sample n totally just overcomes that. And it's the same idea here. This is what makes it an actual central limit theorem. So even if you're looking at the most skewed population ever, say, we had some skewed ones. I think we saw some way back here. Maybe spread might have had some. Let's see, take a quick gander. No, we just sketched them. I think we had some skewed ones in center then. Let's take a look here. We definitely had something skewed in this one. This one was skewed, data on tipping percentage. But sometimes skewed can be violent, like say, oh, we didn't have anything too badly skewed, but let's settle on this one. If this is the problem you're studying, a large enough sample size can overcome the skew that we would expect to see in the population. We expect the underlying population is skewed. If we take a random sample of 20 and get this picture, probably the underlying population is skewed as well. But if our sample size is large enough, we can overcome the skew, and the statistic, the Y bars that we get, are still coming from the normal distribution. So that's the whole central limit theorem in a nutshell, that the normal distribution is not something that describes every single population, but for a large enough sample size n, it describes where Y bar came from in any population with a quantitative variable. So let's turn over to the full statement and read through it. With that picture in context, here is the formal statement. This is the only second concept and the last concept in the entire course we'll put in a box, because again, these are the big results in statistics so far. The properties of the sampling distribution Y bar. When we say sampling distribution Y bar, we mean this picture right here. It says Y bar is the mean of observations in a random sample of size n, where that population has population mean mu, standard deviation sigma. Then the mean value of the sampling distribution of, oh, hang on, that's a typo. That should have said, sorry for that distraction, Y bar. It's described as mu, and that means there's two typos here. Let me fix that one. Y bar. So the mean of the sampling distribution, mu Y bar, is just the mean mu itself. So that's just saying the mean of the statistic Y bar is just mu itself right down below here is what that statement is saying. Next, the standard deviation of the sampling distribution of Y bar. Missed another one. Sorry for the X bars that showed up here. If you're curious, this was a different book that used X bar instead of Y bar, and I've been purging the X bars for quite some time now. So the standard deviation, the spread of that normal distribution we've been looking at, is written as sigma Y bar. And these are the two rules. The mean is mu, like we saw in the graph above, and the standard deviation is just sigma divided by the square root of n. So that gives us the full description of the information. In the above graph, we can fill this in if we'd like and just say this is sigma divided by square root of the sample size. So that's the description of this curve here, the sampling distribution of Y bar. It says even more. If your population is normally distributed, well, that's something that's kind of like a mathematical fiction. Some populations are close to normally distributed, but none of them are exactly normally distributed. That's just a particular mathematical equation. But if it happens to be exactly normally distributed, the sampling distribution is also normally distributed at any sample size. Rule 3 is kind of nice, but it's not very applicable because we look into populations that are skewed or just not exactly normally distributed, just close. So rule 4 is the big statement they were talking about. When n is large, the sampling distribution of Y bar is well approximated by a normal curve, even when the underlying population is not normal. It could be skewed, it could be bimodal, it could be extremely bad, tons of modes, humongous amounts of skew. Try imagining writing down the worst histogram ever, and that's your population. That's okay. Make it large enough, and the normal distribution still pops out. And for an extremely crude rule of thumb, for most populations, at 30 or higher, that's sufficient for the central limit theorem to be applicable. This means it's slightly more forgivable than even the quantitative data in chapter 13. We saw situations where at 147 ceramic hips, central limit theorem was barely effective. We only had 10 successes in the sample. But quantitative data is more forgivable. At sample size 30, for this to not be effective, you have to really come up with something just outrageously skewed, probably something more skewed than we've even seen in the notes. That's something we'll show in class when we come back Monday, a little bit more refreshed. I'll show you a population that is extremely skewed. It'll be a chi-square distribution. We'll see what sample size n has to be to overcome those kind of situations. But this is already a lot of concepts on the table so far. So what we want to start to do is describe our new confidence interval procedure. There's just one big problem first. Recall there's two parameters. There's the unknown mean, and there's the unknown standard deviation sigma. And if we knew what sigma was, that would be the right interval. The confidence interval through the central limit theorem can be calculated this way. One confidence intervals that people used in the past looked like this. Take y bar, add or subtract z star, times sigma over root n. Z star is the same Z stars we were using in chapter 13 with the quantitative data. But we can't actually do that. What is the major problem with this procedure? I think I accidentally gave it away. It's that sigma right here is unknown. Sigma is unknown. So you can't use that procedure. You might say there's a fix to this, right? Because when you have two parameters, you have two estimates, one for each parameter. So what we could do is estimate sigma using S, the sample standard deviation. So this is how we fix this interval. In certain really, really rare situations, you might actually know sigma. And I can think of one example. If you have data that came from IQ testing, that's a rare situation where when you do an IQ test, values are standardized so that the mean is exactly IQ of 100. So after they do the IQ test, they update it, I think year after year. I might be foggy on that, but they're all standardized to have a mean of 100. And I believe the standard deviation is 10 or 15. In those cases, you do know sigma, but that's a really rare situation. In almost every other context, it's a full-on unknown. So we have to make another estimate. So here we deduce the formula for the new standard error of y bar. The purpose of the standard error of y bar is we have to estimate this thing here. This is unknown. And so is mu. This is the thing we want to estimate by using an approximation here. This part right here turns into then the margin of error, just like in the last section. So since this is unknown, it's estimated by standard error y bar. So that's the whole purpose of this thing. In chapter 13, that's what the standard error was doing as well before. So here's our formula. We say standard error for y bar equals, we're trying to write down sigma over root n, but we can't put in that full thing. So we use the estimate. We use the fact sigma can be estimated using S. We wrote above on the notes, just a literal sigma is approximately S. So down here, we'll say standard error of y bar is S divided by square root of n. And that's our standard error. Well, any questions, folks, on that so far?
S was the standard deviation of the sample.
Yeah, exactly. Something went wrong with my text here. Let me fix that. Thought my eyes were giving out for a second there. That was sample standard deviation. So there's still one major problem. And people didn't know about this for quite some time. If your samples are over 30, maybe closer to 100 or something like that, and you just throw S over root n here, and you reuse Z star, your method is pretty accurate. But people started to notice that there was a legitimate problem about this. So let's imagine what the problem could be. Let's scroll up to the top for just a moment. We've been making this complaint for a while, right? We've constantly said that estimating a parameter with a statistic is useless until you can describe to us the error in this approximation. What's the margin of error in making that estimate? But notice what we just did. We approximated sigma with S as well. And nowhere on paper do we have an estimate for that value that we put here. This didn't happen in the last section because there was just one parameter. But now that there's two parameters, there are estimates on top of estimates. There is an extra margin of error baked into the problem. And for a long time, no one knew about this until one guy found out. This is the purpose of those Wikipedia documents on the notes. So just for a bit of a mental break, because we've been looking at technical information for a while, let's look back on the Moodle page or Canvas page back over here. It was William Seeley Gossett who first noticed you can't just estimate sigma with S without incorporating the error in that estimate at the same exact time. And these are the two major figures in modern statistics. Ronald Fisher is an incredible guy. He's known as a genius. He was a polymath, which means he's an expert in a whole bunch of different fields: mathematics, statistics, biology, geneticist, and an academic, whatever that means. He's described as being a genius, and he is really the most important figure in modern statistics that we do today, that we're doing right now. But he's kind of boring. He's just one of those guys that was gifted. He did a lot of work at his time. He's kind of like Isaac Newton or Leibniz, the people who discovered calculus. The guy who's interesting is William Seeley Gossett. I wrote here he's a role model for people in the sciences, and there's a good reason for that. He was kind of just your average guy. He worked for the Guinness Brewing Company. He was considered a chemist because his job was to combine different hops, different barleys to test the beers that they produce at the Guinness Brewing Company. He was working with these same exact intervals that we're looking at here. And he noticed when you just throw in S for sigma, his confidence intervals weren't coming out right. His data wasn't making the predictions that he was expected. It's because he was working with low samples, sample size 4. One huge vat of beer, another huge vat of beer. He couldn't put in 30 of them. Guinness Brewing Company wasn't that rich for their experimental brewing operations. So when your sample size is 4, the error right here is profound and extremely noticeable. And so this one guy, William Gossett, he wasn't even a statistician. He was a chemist at a brewing company. He came out with a new distribution. It's not the normal distribution this really follows. And he wrote to Fisher, and they exchanged a bunch of letters on this. And the reason this is called the student's T distribution, or their student's T tables, is the Guinness Brewing Company didn't allow him to publish this. Other people had published results from brewing that kind of gave out trade secrets. So they told William Seeley Gossett, you can't publish this student T's distribution. But Fisher and him agreed that this is like really important information that mankind just deserves to know, that this is not the right value. Z star isn't correct here. There's more error here. So the reason I say William Seeley Gossett is a great role model is he fought his bosses. He kept coming at them, and he got the Guinness Brewing Company to agree to publish this information. He had to agree to publish under a pseudonym. He published under the name Student, which was just a humble way to refer to himself. He couldn't say anything about Guinness Brewing whatsoever in what he published, but he released this information with the encouragement from Ronald Fisher, and Fisher told him he believed that Gossett had effected a logical revolution, and he really did. This is a profound statement for what we're going to look into. the fact that what goes here is not Z star, it's something else, something called a t-distribution, or sometimes referred to as students. This is Gossett when you see this. Students, t-distribution. So he came up with this from scratch. And that's why when we see the confidence interval formula down below, there's a T star, not a Z star any longer. So our job in the next part of the notes is to see what is the T distribution. It's kind of like when we were way back in, say, section 5.4, and we were looking into, or rather 5.3, we were looking into what are the normal distributions in the first place. We plot a bunch of them to see what they are. We'll do the same thing here. Keep in mind, the whole purpose of the T distribution is to admit you can't just put down an estimate here until you incorporate the uncertainty, the approximation error, the margin of error in making that estimate. So here's what Gossett did. Here's our quick graphs. The blue curve is just the ordinary normal distribution with a mean 0, standard deviation of 1. And we can put a quick graph on this. If we're doing a 95% confidence interval, then we would go from a number that's about 1.96. I'll put it about here. Here is Z star, 1.96, puts up a little bar here, and there's our negative Z star, puts up another bar here, and the area in the middle is approximately 95%. That's how we were getting our 95% confidence intervals. And people were doing it this same exact way in the past. They just threw in a value for sigma using the sample standard deviation and went with this graph. But that's not correct. William Seeley Gossett found the T distribution. This is the right graph. Now, his sample sizes were about 4 and 5. The degrees of freedom is going to be 1 less, so we'll look into that formula as well. We might as well just put this on the picture, that doesn't hurt. DF stands for degrees of freedom. This is something new we have to calculate when we do our new confidence intervals. But it's not so bad. The formula is DF equals the sample size n minus 1. So you get a new T distribution, a curve like the one in blue, but slightly different, at every single different sample size you pick. So if I stop at degrees of freedom 38, that means the sample size was 39. And William Seeley Gossett's sample sizes were about 4 or 5. So degrees of freedom were about 4 or 3. Let's put it on the 3. So this is what the real distribution looked like. It's the green one here. And you know, it doesn't look that bad until you imagine, what is the critical number T star? It's the area under the curve, right? But this curve is heavy-tailed. There's way more area spread out to the far left, to the far right. So if we try to do the same kind of area estimate, here's what we have this time. Under the green curve, to get 95% confidence, you're probably out here. Here's T star. I don't know exactly where it is, but that's going to be its approximate location. We'll compute these from scratch to see exactly where they are. And that's where your 95% confidence is going to come from. This number. It's way bigger. He noticed profound errors in his studies at low sample sizes. But when he derived this curve from scratch, he found the right number T stars, and all the experiments at Guinness Brewing Company came out right. He just needed a wider margin of error. Remember, there has to be a wider margin of error because there's uncertainty right here. You can't just throw in an estimate like that and expect things to work out. So this is the logic of why our methods, on face value, they seem similar, but we make a pretty heavy change. We have to start to compute the new thing, T star for every confidence interval. So let's throw this into the notes just as a place to revisit, to think about this again. So every t distribution has greater variability than the standard normal distribution. The t distribution corresponds to any degrees of freedom. It's bell-shaped, centered at 0, just like the standard normal distribution. But here's where we're seeing the greater variability. T star is greater than Z star. So that's our immediate and direct consequence. T star is greater than Z star. But something else is kind of nice as well. If your sample size starts to grow, this is the reason people didn't notice this at first. A lot of times statistics are being done at sample sizes kind of like this. Notice right at around sample size 30, so degrees of freedom is 1 less 29, these curves look about the same, so the error becomes a little bit invisible. Yet, T star is still bigger. It's going to make our confidence intervals a little bit wider if we still use the right distribution, the T distribution. So even though they look identical, in the quest to be as accurate as possible with data where we're already estimating once already, we have to use the right distribution. But this is a good takeaway as well. At large sample sizes, the normal distribution and T distribution are in fact pretty close. So that's concept 3. As the degrees of freedom increases, the variability corresponding to the T distribution decreases as well. So larger sample sizes means the curves look about the same. But we'll see the difference. We're going to start calculating our T stars to see how different are they at large sample sizes, like say 30 or 100, and you'll see the difference as well. So this is our first stop we have to make. If we're doing confidence intervals for quantitative data, we have to admit we don't know sigma, except in really rare situations. It's almost assuredly an unknown value. So we estimate again, we calculate a standard error, and in order to be as honest as possible, we include the error in making this estimate right here by changing to the T distribution. This has the margin of error baked in, so when we go to use T star, we don't have to worry about estimating sigma and knowing what the margin of error should be for that one. There's a fourth concept that I forgot, but it says, as the number of degrees of freedom increases, the corresponding sequence of T distributions approaches the standard normal distribution. So go higher and higher, and they essentially look the same. But if you're persistent and you zoom in on this long enough, you can spot the difference. And that difference is still important, even at a sample size 1,000, or at a sample size 10,000, and so on. We should always be as accurate as possible. So these are the major ideas so far. Now ready to state the confidence interval. I don't know why my font changed here. That's kind of jarring. It happened on the whole notes. Let me see if I can fix that real quick here. Okay, my font went crazy, but I think everything else is okay aside from that. The whole confidence interval procedure looks like this. We've been hinting at it all along. Y bar plus or minus T star times the standard error of, sorry for that extra Y bar that emerges here, or X bar that was here. Let me put that one in red just to emphasize the change this time. Standard error is quick to calculate. Really the whole thing that makes this slightly tricky is getting the critical number T star. But this is how we estimate the population mean. Conditions just say we need a random sample. The sample size should be large enough to overcome any skew. And this is a good benchmark or a rough rule of thumb. Doesn't mean if we have a sample size at say 10 or 15 that we can't use this procedure. It just means at low sample sizes, we would like a histogram of the sample data to see if the data from the population was symmetric enough so that we could be confident at lower sample sizes. Well, our first job is really to now calculate T star. If we can see how to calculate this part, the critical number T star, then the standard error is just like another formula, and then putting it all together, it's going to feel just like chapter 13. So my spacing kind of went weird on these notes as well. It's kind of strange. So that's what we're going to do next. Calculate a couple T stars. I don't think we have enough time to do a whole confidence interval procedure. So after showing how this goes, we'll see if we're close enough to call it a day. Any questions at all, folks, before we go for this part of the problem? Okay, again, this set of notes, the first part, it's kind of like when we were in 13.1. It's not hard to say what the confidence interval is. It's hard to say how does it work? Why does the central limit theorem do what it does? And in this section, why do we use a t-distribution out of nowhere? But from here on out, it's kind of smooth sailing. We're going to mirror it pretty close to what we did in section 13.3. So let's pull it up one more time, just as a refresher. If you were computing a critical number z star or t star, the initial work is very, very similar. Here's how we did z star. We found out what confidence level we're going to compute. We make it the central area with 0 in the middle. This time it's a t distribution, so we change to t with the right degrees of freedom. And then this is the whole major formula. Area is 1 minus c divided by 2. If you put that in the calculator and you use just the right function, you get your t star values out. So let's show how that goes next. The thing we need to be careful of is there's a second formula, degrees of freedom as well, we have to be mindful of. So we have a confidence level at 90%. If our sample size n is 10, that means the degrees of freedom in the problem. Let's go for a slightly different color coding. Let's connect these thoughts. The degrees of freedom in the problem is going to be abbreviated to just df for degrees of freedom, sample size n minus 1, so it's going to be 10 minus 1 for a value of 9. So we have 9 degrees of freedom in this problem. Next thing we do is we draw something that kind of looks like a normal curve. It's more heavy-tailed, but that's kind of hard to convey by an ordinary hand-drawn sketch, so probably still looks like a normal curve when we write it down. But this is the t df distribution. Every t distribution just depends on the sample size, and so then it depends on the degrees of freedom. That means this is the T9 distribution. The center is still 0, so that's kind of nice in a way. We're trying to capture the central area, 90%. So let's just sketch something that looks like about central 90%. I'll go from about here to my eye. Maybe not perfect, maybe they should be a little bit wider, but it doesn't have to be absolute perfection. This number will be positive t star. This number will be negative t star. And in the middle is 0.90. So take whatever confidence is stated, write it as a decimal, and put it in the center. Then, same exact formula as for before in section 13.3. The area in the left tail and the right tail is just 1 minus the area divided by 2. So go 1 minus c divided by 2. That's 1 minus 0.9. O divided by 2. It's a 0.10 halves, which is a 0.05. And I mean, we probably knew it's a 0.05 if there's central 90, but this was a weird confidence level. That's not a bad thing to just remind ourselves. That's what goes inside here each and every time. So 0.05 goes into that region. Same value, 0.05 goes into this region. And the calculator I'm going to be using only uses the left tail. So I'm going to give it a 0.05, and it's going to give me negative t star. Other people's calculator, you can switch it to the center. And I think we learned from last time, it'll give you both the negative and the positive. Or you can switch it to the right value to get the positive. But here's the next big idea. It's not a normal distribution, right? So we're going to use inverse t distribution. So this is the calculator in the function in the TI-84. So in inverse t, let's call up that function. Starts out similarly like before, hit second vars. Go down to inverse t. So that's the function we want. You know, wouldn't hurt, since this is the first time we're doing this, to put down a bit of a paper trail. So let's put some screenshots down just as a sequence of calculator operations you would take. So here's inverse t going in. Hit enter on that, and it wants two things. It's pretty fast. First thing, it wants an area. My calculator, I have to put in 0.05. Or you could put it at 0.95 and you'd be getting the area to the left of this t star. I think it's simpler to just use this value, get the negative number, and flip it to positive. Degrees of freedom is 9 in this problem. Then here's inverse t. And it's kind of interesting to watch what happens in this calculator. This is pretty old technology from way back, I think late 80s is where this chip is designed in. It actually takes a while to compute this. There would be a little calculation bar that appears right here. Yours might be faster if it's more updated chip, but notice it takes it a moment to actually calculate that thing. So that's kind of impressive. This is a pretty big, robust computation, and we get the number negative 1.8331. This means the t star that we wanted, typically we state the positive value, is positive 1.8331. So that's our critical number we would use in the confidence interval. Actually, let me change the color coding here to highlighted in yellow. 1.8331. Is that what folks got so far in your calculators? Okay, thing to take a note of is that's a huge critical number. If you did the Z-star procedure, and this is what people were doing historically before William Seeley Gossett came around and published this distribution, at 90% confidence, you would have been using this table value. Your Z-star value would have been a 1.645, but that would have been an error. If you did a 95% confidence interval at this value right here, your interval looks narrower, but you're going to notice that your data isn't actually going to fit reality when you go to try to see what happens after you made your prediction. It's because we made two estimates. We're estimating the parameter mu and the parameter sigma at the same time. We get punished for that in a way. Extra uncertainty means a wider confidence interval, and t star going right here is doing just that. It widens out our confidence interval by a pretty respectable measure. Standard error could be a big number, so even though it doesn't seem impressive to go from a 1.645 to 1.8331, if the standard error is big, that change is actually pretty big as well. So that's a computation. Any questions at all, folks, getting that first one down? I forgot to do one thing. We were going to put this in the calculator, or put this as a screenshot. Let me put in one more screenshot here just for good reference. We went inverse t. This is what it should look like before hitting enter. And so that's a reference for the calculator in doing this procedure here. But there's kind of a cooler way to do this. What I would do if I was doing this as a calculator problem, and we do have to do this a good amount, so this is a good shortcut, is go parenthesis 1 minus whatever your confidence level is, 0.90, divide by 2. And my calculator, I have to do that every single time because I can't put in the center value. So if you can change to center on here, you really just have to put in the central value, 0.90 every time, and that works out. In this calculator, that's the hack that makes it work. So hit enter again in that format. Give the calculator a moment and just state the positive value. Well, let's try it out one more time just to get a feel for this. On this one, sample size is 190. This means the degrees of freedom in this problem would be n minus 1 for 190 minus 1, 189. Confidence level is at 99%. So with confidence at 99%, we can say the area equals 1 minus 0.99 divide by 2. And these are the only two things you really need in the calculator. Once you put those two down, T star can be computed just right away. And let's take a quick reference. The sample size is really large on this one. We're at 99% confidence, so we expect a value about 2.58. But it should always be bigger because there's extra uncertainty in this problem. Estimating sigma through the standard error of y bar, even at a sample size of 190, has uncertainty. So this is what it's going to come out in this problem. Hit second bars, go down to inverse t, hit enter, flip this to 0.99, and the easiest mistake to make is to forget to update degrees of freedom. At every different study, every different sample size, it's a new degrees of freedom. Then this is kind of getting into the limit of what the calculator can compute easily. Takes a moment, hit enter, let it compute. And this is our new value. To 4 decimal places, this is a negative 2.6019. So taking the positive value, we'll just make this positive 2.6020, rounding to 4 decimal places. But notice that it's again appreciably larger than this quantity. So 2.60, rounding to that 4th place, that's rounding with carry, my least favorite, but we get 20. So the standard reminder is don't forget to use inverse t. And this is what it should look like in the calculator before going to that last step. Let's put in one more screenshot. Oh, went to the wrong one. That's inverse norm. And it wiped out my result, 1 minus 0.99 halves and 189 degrees of freedom. So this is the moment before you would start hitting the enter key on this problem. So once you get some good practice doing the critical number T star, it's not so bad. The thing that you just have to recall is we have to do it fresh, essentially on every single problem we'll see in this course. Unless for some reason we had 2 problems back to back at the same exact sample size and same confidence level, but that's really highly unlikely. Well, we did it, folks. We now know all the moving parts of the confidence interval procedure. Next thing we'll do is apply it to some real world examples, like example 3. This looks like it's a crime statistics kind of problem. This one's real data. Apply it again to, this one's data on dementia, so that's kind of exciting. And another one for looks like something in nutrition, something about calcium. Well, the big takeaway is our confidence interval changes a lot. Once we go to calculate confidence intervals for quantitative data, T star comes from a whole different distribution. But in our calculator, it's not too bad to calculate. It's just one new thing to add on top. Well, any last questions at all, folks, before we call it a night today? Okay, when we come back on Monday and on Wednesday's class, we'll be doing confidence interval problems. But the next Thursday, I'll do the standard call for exam review questions so we can review for our upcoming 3rd exam. We're not going to go into chapter 14 because we're only just starting it. I think the turnaround's too short to really learn this well and put it on an upcoming 3rd exam. But have a great weekend, folks. Don't hesitate to reach out if any questions come up, and I'll be happy to help. We seem to end at 5 minutes early about every day, it seems like, but you know, it makes sense because this is not a 5-minute problem. This is a good stopping point for us.
I'm guessing when we go to get like the standard deviation of the sampling size, we'll go back to stat count.
Yeah, good call.
Option 1.
We have to do that for some of the data, not in every problem. But this one, they never told us that information. So yeah, you go to stat. Let me try again. Stat, calculate option one after importing the data, exactly. Yeah, so we'll be refreshing that as well for this example four. It'll be 7, 10, and 13. Yeah. And I've got the review material posted a little bit early this time. So the two sample exam versions are posted as well. Well, have a great weekend, folks. We'll be back to it on Monday. Awesome, thank you. Awesome, thanks.
So. I'm looking at this quiz and I got the other, most of the bigger questions done, but it's just
Yeah.
these two simple ones that kept screwing up my mind. It says describe the population of this study using the context.
Gotcha.
So what is it? That's gonna sound stupid, but what does it mean by like that? Why does it ask me to describe it if most of the context is already, it's already described?
Oh, I see what you're saying, yeah. So what I would do to solve this problem is think about what the sample is. They said that there was 30 participants. For the 36 participants, the mean was 84 points. And you go, the 36 participants took their herbal supplement, ginkgo biloba, every day for 90 days.
Yeah.
So this tells you the population, well, the sample came from that population.
Yeah.
So the population would be all people taking ginkgo biloba for 90 days. So we want to know if the sample includes those people, how would the population, what would the population be? The same exact kind of people.
But I can't really put down a number because it didn't.
Exactly. You just have the mean of the sample. That was like, I think the 96 points or 84 points, whatever it was. Yeah, 84.
Yeah.
So that's gonna be the statistic Y bar in that study.
Okay, and then describing the sample study will be about how they grab 36 participants for people who take that supplement every day. for a
Exactly,
month.
yeah.
Okay,
Usually what you do is you describe the population in a lot of detail. You'd say population is all people taking ginkgo biloba for 90 days. And then when you go to describe the sample, you can just say the 36 people selected. Because it automatically, we know the sample came from the population. And once you just say the 36 people selected, we already know that they took the ginkgo biloba supplement for 90 days.
yeah, okay. Yeah, that makes a lot more sense. 'Cause I was trying to find in the notes that we went over. I just couldn't find it.
Yeah, I gotcha.
Alright, well, because I did see one, but like, it was about the number of successes from what population, whether it be all of them, or if it's a sample.
I see,
And,
yeah.
like, that doesn't apply to this.
Yeah, this one is just the population, not like a parameter, like you're saying, yeah.
So like, I was like, I might as well ask them today.
We're glad you asked. Yep,
Got a question about
Sure.
the latest quiz.
yeah.
I left
all
my
the-
sheet on the freaking desk at work. Right here. So originally, when I wrote my unknown parameter, I wrote, so the true proportion of people that had died from cancer among all of those who were exposed to the same level of radiation.
Yeah, exactly.
But would it be better to put working on the film exposed to the level of radiation?
Well, if you're talking about working on the film, you'd be talking about the entire 220 people. So you'd be restricting your population to just those 220 itself. So we
Okay,
want to think of the 220 as sample. We're assuming it's representative sample.
of what? Well, that's where I got confused.
Yeah, it'll be a sample
Was
of,
there more people working on the film?
no, we're gonna just say,
Like that
What-
area?
yeah, kind of like the area. We're gonna say, if we had just about anybody who got hit by a blast of nuclear fallout or radiation from the nuclear test,
Okay,
that's our population. Everybody that might have been hit by the same exact level of radiation. So if you were exposed to that level of radiation, we were thinking of you as belonging to the population.
okay. So I hope that was another good example of me overthinking it,
That's a tricky one too, yeah.
right?
Yeah, I'd say so.
Okay.
And that's good to do because sometimes these populations are really hard to nail down on paper. And it turns out there's a little bit more to that study that was really in the problem that we wrote.
Yeah,
A lot of people died to cancer in that particular film crew, but they found confounding effects because back in the 40s, if you were on a film crew, you're basically a chain smoker. And so a lot of these were just lung cancer deaths as well. So there's more to the story that we really can see just from that data itself. There's a lot going on in there. But analyzing it on face value, we're going to just think of the actual radiation from the nuclear blast as being the main effect.
yeah. Very interesting. One of my, so I'm taking this class in English right now. In my English class, I'm writing, the topic I chose was like ketamine therapy for depression and PTSD.
That sounds like a fun one.
And, as I'm doing my research, I've seen a lot of, I don't know if it would be quantitative or categorical data.
Might be a mixture.
It's like people that have had the treatment, that have had their symptoms lessened, I guess,
Mhm.
or it has been effective. I guess it would be categorical if it's like effective or not effective, right?
Yeah.
I mean, it's categorical.
And then depending on how they describe their symptoms, they might say, maybe on a sliding scale of 1 to 5, how were your depression symptoms reduced? That could give you quantitative like values, or it could also be analyzed in a categorical way as well. So those can turn into pretty complicated studies.
Yeah, I just have noticed there's a lot of that in that specific area. There's a lot of studies that have numbers and shit.
Yeah,
I was thinking about forwarding them to these to PCAL.
I'd be happy to take a look. Yeah,
This was interesting, you know?
it is. And it's kind of cool to see how it might connect to what we're doing as well in this class.
Yeah, I mean. Yeah, I get a lot more out of school now that I'm like paying for it myself.
Yeah, I hear you.
In it, you know?
Yeah.
So I couldn't imagine going to college back when I was 18, but.
Now, I tried back when I was, let's see, 19, and I just failed out the first semester, failed out the second semester, and they just kicked me out. I went back at 25 where I was a little bit more serious, paying with my own money now because, they take away your ability to get a student loan after you got academically dismissed. So, yeah, I know that experience. When it's your own money and you're a little bit older, you take it way more serious.
Yeah, I've just noticed that I do apply myself a little bit more back to when I used to party, you know?
Yeah,
So. Yeah, have a good weekend.
you too. Take care.